Welcome to part 3 of a series of videos about multivariable calculus using the computer program that you see here called Mathematica to both do calculations and visualize things that we're doing here. My name is Bill Kinney. I'm a math professor at Bethel University in St. Paul, Minnesota. This is also part 3 of a sub-series called Calculations with Parametric Curves. What we've done so far is we've been given some functions that define what are called parametric equations, and we've used Mathematica to graph these parametric equations to try to see and model some motion, in particular motion of a bug. In this video we're going to do something different. We're going to parameterize, we're going to decide what functions to use to parameterize straight line motion at a constant speed. We will continue making use of parametric plot and manipulate, which are two commands that I've shown you so far. But two new commands that I will show you in this video are the commands list plot and show. So here's our example. We want to find, we're not given this time, we want to find a system of parametric equations, and ultimately two functions, in fact, that models the motion of an object moving along a straight line at a constant speed, starting at a certain point, 5, -4, when time is 0. T is time, it's the parameter, and ending at a different point, -3, 2, when t is 1. So after 1 second has gone by. Then we want to graph the parametric curve that results. It'll be a straight line at traced out at a constant speed. Also, we want to find at the end the distance traveled and the speed of the object, assuming distance is measured in meters and time in seconds. Alright, so think about this for a minute. What kind of functions should we use to create our parametric equations to model straight line motion at a constant speed? Think about that. I hope you would guess that the functions you want to use should be linear functions. It's along a straight line, that's one hint, and it's at a constant speed, that's another hint. Actually, you can use nonlinear functions, and in fact we've done that already in the first couple videos, to model straight line motion, but not at a constant speed. Sometimes nonlinear functions model motion that's not along a straight line as well, but we have seen an example with the bug of straight line motion not at a constant speed with nonlinear equations. But when you want a constant speed, we want to use linear equations. I'm not proving that these will work, but this should seem reasonable that linear functions will be what we want to use. We're starting at the point 5, -4 when t is 0. We know that f of 0 is going to be b, its constant term. G of 0 is going to be d, its constant term. This means that, in fact, b must equal 5 because it's the x-coordinate. F of t gives you the x-coordinate, and d must equal -4 because g of t gives you the y-coordinate. So we know b is 5 and d is -4. What about a and c? Well, look at that. Those are numbers that are in front of the t. Those are the rates of change, thinking along calculus lines, of these functions with respect to time. They are linear functions, so it's going to be a constant rate of change. Remember that delta x represents the change in x. Delta t is going to represent the change in t. I'm calculating the ratio delta x divided by delta t. What is that going to give me? That's going to give me a. That's going to give me the rate of change of x with respect to time. How do you calculate delta x? What's the change in x? Well, x starts at 5 and goes to -3. So the change in x is -3 minus 5. What about the change in time? Time starts at 0 and goes to 1. Delta t, the change in time, is 1 minus 0. -8 over 1 is going to be -8. Since that ratio is -8, we can say that a is -8. Also, d is going to be the rate of change of y with respect to time. Delta y divided by delta t. Y starts at -4 and goes up to 2. Y increases from -4 up to 2. Delta y is 2 minus -4. delta t is still 1 minus 0. So we get 2 minus negative 4, which is 6 divided by 1. We're going to get 6 for d. So our answer is x equals f of t equals at plus b. That will be negative 8t plus 5. And y will equal g of t. That will be 6t minus 4. That's our system of parametric equations that defines the motion that we want here, straight line at a constant speed. Let's now use Mathematica to model this. I'm going to type in the functions. F of t is negative 8t plus 5. G of t is 6t minus 4. I've talked about how to enter functions into Mathematica before. I will again emphasize that I can create a point-valued function if I like. C of t, which is f of t comma g of t, inside a list in Mathematica, and you specify a list with these curvy braces here. And let's do what we did the last time. Let's make an animation of the motion. Manipulate makes animations. We need an animation parameter, which I call b. That's going to start just barely bigger than 0 and go up to 1. That's the second input of the manipulate command. The first input is going to be what I'm going to plot. Initially I'll make a parametric plot. So I'll just do parametric plot like this. I'm going to add some extra things in here too. I'm plotting c of t. T goes from 0 up to b. And let's make this thick blue this time to show you that we can do a different color. Alright, again, this is not going to be quite ideal. We'll see some non-ideal things about it, but I'll go ahead and hit enter here, shift return. You see right away it's a very small piece of the curve, and the scales are going to change as we go on here. It's running a little slow here on me. Hang on. Let's pause it. Here's the final curve. We started at the point 5, negative 4, and went to the point negative 3, 2. 5, negative 4 is down here in the lower right. Negative 3, 2 is up here in the upper left. So we were traveling from lower right to upper left. But it was a very jerky kind of motion. We want to keep the plot range, the window, constant. I also want to add a few other things to this. I want to make a dot where the object is. So what I'm doing is I'm embedding this parametric plot inside another command called show. Show is a command that combines different graphic objects in Mathematica. I want to use another command called listplot also within the show. Notice both parametric plot and listplot are inside the show. Parametric plot plots the curve. Listplot is going to plot a point, a dot. I want to combine those two graphics with show. You see they're also separated by a comma. I want to graph the point C of B as B changes. That will just graph one point for different values of B. You need to put it inside curvy braces like this. And if I add the option plot style arrow, let's make it black, and point size 0.02, that will make it nice and big. There it is. But we need to add some other things to make this more ideal again. We need to keep that plot range constant. I can do that within the show and outside of the parametric plot and list plot. That's probably the most ideal way to do it. So I'm going to put another comma right here and plot range. Let's go negative 10 to 10 in both directions. Let's also label the axes with axes label. X and Y, and I'll make those bigger. There is something still that's not quite ideal here, and that is the fact that if you notice, look at this carefully, the axis is shifting. The origin is not in the right spot until the end. I'm not quite sure why Mathematica does that sometimes, but you can fix it by adding another option, comma axes origin arrow 0, 0 in a list. That will keep the axis fixed, the origin fixed at the same point all the time. The axes are going to intersect at the origin. There's the motion. You can see it's straight line at a constant speed. What is the speed? What is the distance traveled and the speed? The distance traveled we can get by the Pythagorean theorem. It's going to be the square root of the horizontal distance traveled, which is 8. Comes from the slope there, and we're doing it over 1 second. And the vertical distance traveled is going to be 6. The square root of 8 squared plus 6 squared. That will be the square root of 64 plus 36, square root of 100. How about that? Nice number, 10 meters. Since it's over 1 second, the constant speed will equal 10 meters per second. Alright, the distance traveled is exactly 10 meters and the constant speed is 10 meters per second. That's the answer to the last question here. To end the video, I will now show you your exercise to try on your own. So pause the video, write this down, try to solve it. And then my solution is down here. The functions you should get are these two functions. F of t is negative 10t plus 6, g of t is negative 16t plus 7. The distance traveled is about 18.68 meters. The speed is 18.68 meters per second. And here's the motion. This motion is from upper right to lower left. Okay, and that'll end this video.